So as you can see, the title of the talk is Quadratic Twist of Epsilon Factor of Symmetric Cube Transfers of Modular Forms. So first I will introduce what does it mean by epsilon factor. Then I will talk about quadratic twist, quadratic character, and then we'll talk about symmetric cube transfer, and then we'll state the main results. Let's start with a number field. That means a finite extension of the field of rational number Q. You can you can take for the rest of the talk that F is equal to Q, but whatever I'm going to define, that holds for any number field. So consider the ring of adels, which is denoted by AF. So, so the elements of AF are tuples XV, such that each XV is coming from FV, where FV is the completion of F at the prime or place V, such that XV is belongs to the ring of integers of FV for almost but finitely many finite prime V. Next, consider the maximal ideal of the ring of integers OV, which is denoted by PV, and consider and QB denotes the cardinality of the residual field. Now this is a ring AF. We can consider its group of units, which is called ideal group. Now consider a character of the ideal group, which is called Hecke character, such that it is trivial on F star. Then this character has a decomposition as chi v, where each chi v is a character of the multiplicative group of FV, such that chi v is trivial for all but finitely many. Chi v is trivial for all, trivial on OV for all but finitely many V. Okay, now fix a place V. And consider the additive group FV, and consider additive character phi V. For now, take phi V to be non-trivial. Then take associated the local epsilon factor with the local L function by this formula, where LS chi V is the local L function associated to the character chi V. Now, by definition, LS chi V is 1 over 1 minus chi V at uniformizer into QV to the power minus S if chi V is unramified. And if chi V is ramified, then this is 1. Now, and this is multiplied with a gamma factor, which depends on the additive character and the multiplicative character we have started with. This is a rational function on QV to the power minus S, and this satisfies some other conditions also. Now, Tate showed that this is an exponential function. That means an entire function. It does not have any zero and pole on the complex plane. He also proved that the epsilon factor of chi v and of chi v inverse is related by this relation. Now, if we consider chi v such that chi v equals to chi v inverse, then the value of the epsilon factor is plus minus 1. And from this formula, we can see that it is enough to focus on the epsilon factor at the complex number is equals to half. Now, if I take the product over all places, then we get the global epsilon factor, and Tate proved that the global L function of chi and chi inverse is related by this global epsilon factor. And from this, we can see that the global epsilon factor does not depend on the chosen additive character. It only depends on the Hecke character we have started with. So here, till now, we have talked about epsilon factor attached to a one-dimensional representation. So this theory were generalized by Goodman and Jackie for any local representation of GLN for arbitrary n. So we have this multiplicative character chi phi. Let a chi phi be the conductor of the multiplicative character. That means by definition, this is the smallest positive integer such that chi phi restricted to this unit group is 1. We attach another integer with the additive character, which is called level of the additive character, which is integer, which is an integer such that this satisfies this condition. Now we have a nice formula for the epsilon factor. So this is this formula is at half. And here it can be written as a finite sum. Here the x, x varies over the representative of this group. And this is well known that this is a finite abelian group. In fact, if we take f to be q and v to be any prime, like f to be q, and if we take qp and p odd, then this is actually a cyclic group. And also it can be shown that this is independent of the chosen representative. And here this C comes into the picture where C is a non-zero element of FV, such that it has valuation sum of these two numbers. This epsilon factor has some nice properties. I'll mention only two of them that has been used in our work. So the first one is if we twist the character chi phi by an unramified character theta v, then the epsilon factor of chi v and theta v and the epsilon factor of chi v differs by this quantity. Here, so only the theta comes out. Here pi v is a uniformizer of FV. And now if we take a finite extension of QP, and if we take a character of K star, then we can use the Artin isomorphism and can get a character of the Wei-Lilin group WK. And if we take the induction of that character, we get a representation. So on the Wei-Lilin side, we can also attach an epsilon factor. And this formula says that we can just get the value of the epsilon factor by the formula that we have defined above. But here we have to take so here the additive character phi is additive character of QP, but we have to compose phi with the trace map. So next I'll talk about quadratic twist. So start with an odd prime P, and then P star is either plus P or minus P, depending on the legendary symbol -1 over P. In that case, this is a quadratic extension, and this extension is ramified only at P. Each quadratic extension will give a quadratic character. So take the quadratic character chi that is attached to this quadratic extension. So this character can be defined by the Kronecker symbol, and one can idealize this character chi. So that means we'll get a sequence of character chi q of the multiplicative group, and it has explicit. We can write it explicitly what this chi q will be. If q not equals to p, then chi q will be unramified, and at q it will have a value. It will have value, given by the legendary symbol. And if q equals to p, then the conductor of chi p is 1, and this chi will factor through the unique quadratic character of the finite group fp star, and it will have value 1 at p. So next start with a modular form, cusp form of weight k level n and weight k level n and event type is epsilon. Write n as p power np into n prime, such that p and n primes are relatively prime. Let pi f be the attached automorphic representation. Then we have this decomposition of pi as irreducible admissible representations of GL2QP. Now, from the classification of irreducible admissible representations of GL2QP, we know that this is either principal series, spatial, or supercuspidal representation. So we, okay, so now consider this number, epsilon p, which is ratio of the epsilon factors. So this is pi, epsilon factor of pi p twisted with chi p that we have discussed earlier. And this is epsilon factor of pi fp. So here I haven't written any additive character, but there is an additive character in both the component, and we need to choose the additive character. We need to choose the same additive character in both the components. Now the point is why twisting by a quadratic character? So so as I was saying that when chi p is ramified, the L function is 1. So when pi p is ramified, the L function attached to pi p is 1. So the L function does not give much information about the representation, but the epsilon factor can give some information about the representation. And by converse theorem, it says that we can get information about representation by twisting the representations by characters of the local field. So here we have chosen the most the easiest case, the quadratic character. You can take any character and study this number, and that is supposed to give some information about pi p. So in 2013, Passetti studied this number, epsilon p, and he individually calculated the value of epsilon p for principal series, spatial, and supercuspidal representation. And using that, he deduced this following theorem. He says that if we start with a new form f of weight k level n, and for trivial Neven-types, and suppose p divides n be an odd prime with pi p be a ramified supercuspidal representation, such that means pi p is coming from a character of a quadratic extension of QP. Then the quadratic extension will be of the form QP root p star if the ratio of the global epsilon factor equals chi p in prime, and it will be if the ratio of the global epsilon factor is negative of chi p in prime, then it will be the other one. So delta is some non-square of QP. Now, these results were generalized for arbitrary Neven-types by the Mondal and Banerjee in 2020. Next, I will talk about symmetric cube transfer. So start with a cuspidal representation of GL2AQ denoted by pi. So it has a decomposition pi p. So next consider using local Lagrange correspondence, we get two-dimensional representation attached to this pi p. You have irreducible admissible representation of GL2. We have this side continuous semi-simple two-dimensional representation of the Wade-Allen group. So we start with a pi. So you have this pi p. Now for a prime p, consider pi p. So pi p is a representation, irreducible admissible representation of GL2QP. So this is the local Lagrange correspondence. So using that, we get a two-dimensional representation, pi p, which is I should write it. The Wade-Allen group is denoted as WQP prime, GL2C. Next, consider third symmetric power. So that is a representation of GL2C. So how do we get this same cube? So we take the standard representation of GL2C, that is by left multiplication, then we do the symmetric cube transfer. It has a nice matrix representation, which I will not write. We do this composition of 5, then we get a 4-dimensional representation. Now we come back with the local Lagrange correspondence. Okay, maybe I should have written here for any n. I think you will understand. So this is a 4-dimensional representation. So using again local Lagrange correspondence, we get a irreducible admissible representation of GL 4QP, which is denoted by sim cube pi p, and then define sim cube pi as the tensor product of pi p. Now, this sim cube pi is an automorphic representation that was proved by Kim and Shahidi in 2002. Now, fix a prime p, fix an odd prime p, and consider the supercuspided representation pi p. So the Wedel side, for pi p we have phi p here on the Wedel side. So that phi p will look like induction of a character of a quadratic extension of QP, such that the character does not factor through the norm map. Okay. I should write it as phi p, but but I have written it pi p. Yes. Okay. Yeah, yeah, that will be phi p, but I have written here so that people don't get confused. Yeah, so the phi p will look like this. Now, if I do the symmetric cube transfer, this is sim cube phi p, but I have written as here the sim cube pi p. So the Wedel side, if I do the calculation, it can be shown that this will be sum as two-dimensional representation. And from the irreducibility of this representation, we'll get that this representation is always irreducible, but this one may or may not be. And depending on the reducibility and irreducibility, we say that the representation sim cube pi p is of type 1 if this is irreducible, but isomorphic to this one. We say that the sim cube pi p is type 2 if it is irreducible but not isomorphic, and otherwise we say sim cube pi p is of type 3. That means this is reducible. So again, let's start with a new form of weight k level n and Neven type as epsilon. So let 5 is the attached representation to F. Then we study the epsilon. We study the ratio of epsilon factor of symmetric cube transfer twisted by a quadratic character that we have defined earlier. And here, also we have chosen an additive character. In our case, we have taken the additive character to have level -1 in numerator and denominator both sides. But since the phi is fixed, so I haven't mentioned it here. Now we have started with a new form, but for the rest of the section, I will take consider the special type of new form, which is called P minimal new form. So if we start with a modular form, and if we twist it by Dirichlet character, the level of the twisted, yeah. So if call the digital character mu, then if tensor mu will have a level divides n into m square. I mean, the level may increase. So I want the modular form to have the level smallest after twisting by all digital characters. And we call that modular form to be P minimal. So the next results is, so we have calculated these values of epsilon P for principal series, spatial and supercuspidal representations. So let's start with a minimal new form and let AP be the Pth Fourier coefficient. Here P is such that P divides the level of the new form. And suppose that pi P is ramified principal series, then we have these values for epsilon P. I have only mentioned what the values here for P greater equals to 5, but we have calculated for other cases also. Here the third power of the Fourier coefficient appears. We have also calculated the epsilon P, the variance for the spatial representation when P greater equals to 3. And these are the values of epsilon P for supercuspidal representation. So here I have mentioned only for the ramified supercuspidal representation, but we have values for unramified also. Using this, this is the main result. So let's start with an odd prime P such that pi P is a supercuspidal representation. So the Bedelian side will look like the induction of a character of a quadratic extension. Let NP is even. So NP is the P power, highest power of P, which is even. And then it is well known that in that case, K is an unramified quadratic extension, which is given by QP zeta P square minus 1. This is the P square minus 1th root of unity. Under this condition, we have that this sim cube pi P is of type 1 or type 2 that we have defined earlier. What does it mean by that? If the ratio of the symmetric epsilon factor, global epsilon factor is this quantity, and it will be of type 3 if the ratio is this quantity, where the M prime is the prime to P part of the conductor of the global representation, sim cube pi F. And these number S1, S2, S3 are elements of the non-zero element of K with valuation this. Also they satisfy some properties. And now if here we have taken NP to be even, and it is known that this is unramified quadratic extension. If we take NP to be odd, then it is also well known that this is ramified. Next, assume that 3 divides the level of the modular form, and let the conductor of chi cube is greater equals to 3. So chi is this character. Also assume that this is odd, and sim cube pi F3 is of type 1 or 2. Then K will be Q3 root minus 3 if the global epsilon factor is chi 3 of M prime, and Q will be Q3, the other one, if the ratio of the global epsilon factor is minus chi 3 M prime, where again, delta is a non-squared element of Q3, and M prime is the prime to P part of the conductor of sim cube pi F. We have also similar classification for the ramified extension, also ramified extensions when sim cube pi F3 is of type 3. These are all. These are the references. The paper by Passetti that I was talking about. You can find this work in archive.
Thank you very much for your talk. Are there any comments or questions? If not, I think we can thank the speaker again.